Dear ladies and gentlemen, my name is Alexey Slunyaev, and I would like to present you a joint work on numerical simulation of nonlinear waves on the surface of a sea. It's a joint work with Anna Kokorina. We are both affiliated by the Institute of Applied Physics and Nizhny Novgorod State Technical University in Russia. And the first part will be about the simulation of unidirectional waves. And as initial condition, we take random waves which satisfy the Johnson spectrum and have a period of 10 seconds. And then we simulate them under the conditions of infinitely deep water by means of the hydrospectral method, which solves potential error equations and takes into account up to 4 wave interactions. Our domain is periodic in space, and the length of it is about 10 kilometers, what corresponds to about 60 waves. And then we solve them for 20 minutes, what corresponds to about 120 wave periods. And here you can see a surface, which is an example of such a simulation. This is 10 kilometers by 20 minutes. And C state is composed, one C state is composed of from 100 to 1,000 different realizations, different simulations. And by this mean, we obtain the sufficient amount of data to consider to perform statistical analysis. But our main objectives are the detection of rock waves. We specify them according to this criterion that the height of a rock wave should be at least twice higher than significant wave height. Then we also plot probability distribution functions, and the focus of the present talk is on the variety of rock wave shapes. The simulation of unidirectional waves is already published. You can see the references and details are given there. But in this presentation, I will speak only about the shapes and a little bit about lifetimes. So these are two samples of snapshots of rock waves. The individual waves are given by bold. They are specified according to the zero crossing method. And you can see waves at different instants of time. This is one case. Another case, you can see that rock waves can have different shapes. And we distinguish 4 types of shapes of rock waves. First, according to their vertical asymmetry, with respect to the height of a crest and the height of a trough. And then horizontal asymmetry, which is specified by the location of the crest and trough. Who is going first? There are 2 pies of these proportions of 4 kinds of waves. First pi is plotted for the HS 3.5 meters, which is the case of relatively small nonlinearity, and steeper case is given here. And you can see that so there are snapshots of these shapes of waves. So this is 0 level, and this is high crest, and the trough which follows. This is by red is direction of the propagation of the wave. This is another shape of a wave. Again, the crest is higher than the trough, but it is behind the trough. And 2 other shapes are given here by a small number of waves. You can see that when the steepness is high, that the portion of waves with high crests which run in front of the trough, it dominates. It is 61% against about 34% of waves with high crests, which follows the trough, and small amount of waves with deep trough. So therefore, in this case of steep waves, we can see vertical asymmetry, so that the number of waves with deep trough is small, which is typical for Stokes waves, and it is not surprising. But also we see the symmetry with respect to the horizontal line, that the number of rock waves with crests which are in front of troughs, it is significantly higher than the waves with the opposite orientation of troughs and crests. At the same time, you see that if the nonlinearity is not so large, that the amount of waves with crests, with large crests in front or behind the trough, they're about the same. So this is a strongly nonlinear effect which we observed in the direct numerical simulations. And it was surprising for us, and we were happy to observe a very similar numbers in the publication by Ferreira with colleagues in 2004. They analyzed the in situ data of waves measured near the Brazilian coast. And we applied up-crossing and down-crossing method for analysis of individual waves separately, and we obtained a different number of rogue waves. And these numbers are very similar to the numbers which we obtained, which is, of course, a sort of stroke of luck, but nevertheless, this observation in the natural conditions, it confirms what we see. It is not just a numerical artifact, but it is what can be observed in the real sea. Since we have detailed information about waves, we are able to plot such XT diagrams by this color. You can see how this traces how large waves propagate. And blue circles, they show rogue waves. We specify them according to this criterion that the height is at least twice higher than HS. And we say that if rogue waves appear not far from each other in the space and time, then we join them together and call them a rogue event. A rogue event seems to be a more natural object to be studied from physical point of view. And we evaluate the lifetime of this rogue event. And this is a plot of lifetimes of all rogue events with respect to the height over HS. You can see that the higher wave, the higher rogue wave is, the longer it lives, and it is really long living waves. They can live for 50 wave periods, what corresponds to about 10 minutes. They are really long living structures. The second part is dedicated to directional waves. We are doing almost the same, but now waves may be directional. As initial conditions, you use Jones-Webb spectrum with 10 seconds waves, a different gamma, and random amplitudes and phases. And our significant wave heights from 3.5 to 7 meters. Directional spreading is specified according to the cosine square distribution with different angles. We have few simulations of very narrow angles, but typically we consider angles 12 degrees and 62 degrees, which are the same as in the paper by Xiao with colleagues in 2013. And recently we simulated conditions with even greater angle between directions of waves, so that in the last case with the angle 180 degree, some waves may propagate almost opposite to the other waves. You can see two snapshots of initial conditions. This is long crested waves, short crested waves. We simulate these initial conditions by means of the hydrospectral methods as before, and the domain corresponds to about 50 by 50 dominant wave lengths, and we are simulated for 20 minutes. So next we need individual waves, how to obtain them. We are doing this following zero crossing method, but before we cut the surface at each instant of time into many slices along the dominant wave propagation. And then for each space series, we apply zero crossing and then obtain individual waves. We select rogue waves, which are twice higher than HS, and for a given rogue wave, which is shown schematically here, from blue point to blue point, we have a crest and a trough. And so also we specify vertical symmetry depending on if a crest is higher than a trough or opposite, and also the horizontal asymmetry is controlled by the location of the trough with respect to the crest. Is it behind or in front? So again, we have four kinds of waves. And to check that our procedure works properly, first we simulate linear waves. And there are two cases. This is the description of our coding. Let denote type of simulation: L for linear, A small steepness, E for large steepness. The upper index corresponds to gamma. The lower index corresponds to the theta, which controls the spread of directions. And in brackets, this is the number of events which is used for the with statistical analysis. And we can see that the portions of waves of different shapes is about the same, about 25% in linear waves, with different angles of directional spread, 12 and 62 degrees. And so the mistake and evaluation of this portion is plus minus 2%, so which is quite good, we assume. And now we simulate nonlinear waves. First simulations of waves, so first line, it corresponds to HS 3.5. It is small steepness. This is unidirectional waves, long crested waves, 12 degrees, and short crested waves, 62 degrees. You can see that the amount of waves with high crests is larger than the waves with large troughs. And a little bit, this amount grows when we increase directional spread. The second line corresponds to large steepness, HS from 6 to 7. This is unidirectional waves, this plot I showed you previously. And this is for long crested waves, which is almost the same. And for short crested waves, you see that the portion of waves with high crests, which are in front of the trough, is even greater. They correspond to 3/4 of total rock waves, which we obtained in our numerical simulations. If we further increase the directional spread, what will go on? So this is the spread 62, this is 90 degrees and 180 degrees. Again, small nonlinearities on the top. You can see that the evolution from left to right is almost absent, just a little bit within the accuracy of our estimation of the statistics. But if you consider steep waves, we see that for waves with angle 90 degrees, still the amount of waves with high crests, which is in front of the trough, it is very high. It is about 3/4 of the dominant number of waves. But if we consider very broad spectrum and angle, then there is some smaller amount of waves of this sort, but still there is a clear asymmetry with respect to vertical orientation of crest and trough. And this is the summary. So the red, it is what we saw in the first slide, and the blue on the second slide. You can see how all these diagrams evolve when we increase directional spread or increase steepness. So this is the general picture what we see. And you can see that in these cases, the amount of waves with high crests in front, it is really huge. And again, since we have much information about waves, we were looking at the evolution of rock waves, how they evolve. So you can see these are several snapshots of the long rock wave event. It lasts for 40 wave periods and corresponds to long crested waves. This is first moment of time, second, third, and fourth. You can see that these symbols, they show rock waves, and the direction of this small tick, it corresponds to the orientation of the wave. Is the trough behind, or the trough the trough is in front of the wave? You can see that very different shapes may be observed. And in the situation of short crested waves, the situation is even more complicated. You see that the patterns, they are very confusing, but still the event may live very long. This is an example when rock wave was living for more than 20 wave periods. And it is 20, well, it is really large. And in the end, we also obtained statistics of rock wave lifetimes. Since I'm pressed in time, I cannot describe it in details. I just show you this picture that there are different realizations, different conditions are shown here. This is the probability of the observation of the lifetime of a rock event. And this is the lifetime scaled by peak period. And you can see that indeed rock waves can live very long for 60 wave periods and even longer. By these lines, they correspond to unidirectional waves. Symbols correspond to the directional waves. And this is a blue dashed line. It is linear solution. For a linear case, you can see that this is exponential distribution of lifetimes, but depending on the conditions for directional and unidirectional waves, you can see that curves may be above a linear solution and below linear solution. They are above if conditions are strongly nonlinear and the angle spread is small. But if the condition, if the angle is broad, if we okay, the directions of waves are very broad, are very they may be very different when ROG events leave extremely short. So there are conclusions. There are two sorts of conclusions. First, about shapes, that vertical and horizontal symmetries increase when waves are steeper or have broader angle spectrum, but it is until some limit. And for particular conditions, HS 7 meters with peak period 10 seconds and theta from 60 to 90 degrees, 3/4 of ROG waves are represented by crests, which are higher than troughs, and with troughs which follow behind. And about lifetimes, we see that it is a distribution of lifetimes of ROG waves exponential in the linear framework. And it may be, it approximately agree with the linear limit for short-crested waves, or maybe even below the linear distribution if the waves are very much short-crested. And ROG waves under the conditions of large wave steepness and narrow angle spectrum can last remarkably long. This is all. Thank you very much for your attention, and we are open for questions.